as I was already introduced and the presentation was introduced, I will present the topic of my PhD, which is geometric algorithms for the visual exploration of spatiotemporal data. Let me start with the motivation. Why do we actually need all of this? So in research, we often have large data sets and people want to explore this data. One example of large databases is GBIF, which is a database on animal observations, animal occurrences, where each occurrence of a bird, for example, a goose, is associated with other data. So it's not only the type of bird, but it has additionally the spatial location and, for example, the timestamp stored. And these large data sets or databases are not so useful if you cannot know what is inside and you cannot explore, for example, what kind of data is there and the patterns. So data exploration is key in order to get an overview or to understand data patterns or data characteristics. And this is especially important since the amount of data grows all of the time. So in the last years, the number of data sets grew every year. And what do we need in order to allow people to explore the data? We know that visualizations help to understand patterns. And naive visualizations, as the one you can see here, might not be sufficient for these kind of large data sets. So here, all of the data points are represented single by single, and this visualization leads to a bad map readability. So we need different tools to allow data exploration. And what do? We use techniques from cartography, as for example, the generalization to enhance our visualizations. Because this is not the first time that people work on large data sets, so we can use existing techniques. And one existing technique from generalization is the simplification that we will use, or that I will use later on in this presentation, and the aggregation as well, and also the selection. So what are these three kinds of tools? The simplification is visualized here on the left-hand side in the leftist column. So you have, for example, a complex polygon, might be a building footprint or something like that. And the generalization cuts off pieces of it so that it has fewer vertices. In the middle, you see the aggregation. There you might have lot of observations of birds, as we've seen before, all of these single points, and they are generalized, so they are summarized into one object, a polygon. And the last thing that we will use is the selection. So you might have, again, these multiple events or points, and only a selection of these is visualized, and they should represent the whole data set. The structure of my thesis is as follows, that I have two parts. In the first part, I look at spatiotemporal events. So these are events that have, or this is data that has a spatial and a temporal component. And in the second part, I look at spatial-only data. There I looked at polygon simplification, as you can see here on the right. So the blue polygon is the input, and I showed in my thesis how we can design tools to simplify the shape of the polygon. Today, I don't have that much time, so I will only talk about the first part, the spatiotemporal events. So, visual exploration of spatiotemporal events. Now let's again talk about what is a spatiotemporal event. In my thesis, I looked at spatiotemporal events that consists of a point location and a timestamp, and there's some data associated to it. So it's that kind of data that I showed in the very beginning, of the GBIF database, where you have bird observation associated to a point in space and time. This is the database that I showed in the beginning. And now, of course, we are not the first ones who design tools for spatiotemporal events. So let's look at what kind of tools are there to explore these kind of spatial and temporal data. What people do, since we do have interactive devices like computers, we allow users to interact with the visualization. And typically, we allow users to visualize only the data in certain time windows. So here you can see on the left, the first time the user sees the interface, there's a visualization of the data between 1900 and 1940, and then the user can interact with it and look at the data between 1900 and 1990, for example. So now we know how the interface could look like, but what is actually the visualization? So what is the visualization of data between 1900 and 1940 and for the second time window? And also there, we can use existing techniques of visualization of point sets, because for each time window, we do now only have a point set instead of an event set. And there exist a lot of different techniques to visualize point sets. I showed a couple of them here. So there are, for example, alpha shapes, the OHAL, which has these restricted directions, characteristic shapes, and vernacular regions. And we will later on talk about alpha shapes again, so I highlighted them here. But there are also other visualizations of point sets, which are based on grids, for example. So here's the S shape, the grid-based spatial density map, binned heat maps, and continuous heat maps. And here again, we will see the grid-based spatial density maps later on again. So now, knowing what kind of interface we have and what kind of visualization we have, let's look at a real-world application that actually uses this kind of tools. So we have this GBIF database again, and there's the visualization for 1900 to 1940. And after the interaction, the visualization of all data that lies between 1900 and 1990. So here you can see the change in the visualization after the user interaction. And I will show you a small video. So here you can see the actual interface. And as the user changes the time window, you can see the change of the time window in the bottom here. The visualization changes. But what you can also see is that it takes always quite some time until the web page responds and gives the visualization for the new time window to the user. So what we actually have is that there's the challenge of real-time performance. So especially for large data sets, we need efficient response times. And this is established approach, which is used or which also works for small data sets, does not work anymore for these kind of large data sets. We cannot give the time window query, so a query proposed by the user to the event set, compute the visualization on demand, and give it to the user because it's just too slow. So what else could we do? We use a technique that is, or we don't use it. We got inspired by a technique from Bannister et al., which is a time window data structure. And that actually was designed for reporting convex hulls. But the idea is to pre-process the events into this data structure and then report the convex hull fast. And especially, their algorithm is output sensitive, meaning it does not depend on the number of events that we have overall, but it depends on the number of events that are in the output. So this is heavily different, because we might have a very small convex hull, but a huge amount of events. So my research question was, can we develop time window data structures for visualizations of events with a low query time and a low memory consumption? I talked already about the low query time, but I haven't said too much about memory consumption. But of course, we don't want a data structure that is huge only in order to reduce query time. So that is not a good approach as well. We want to have both low query time and low memory consumption. So in the following, I will now present three of my topics: the polygonal representation, afterwards the grid-based, and then the labeling approach. I'll start with the polygonal representation. And we called this data structure then the alpha structure, and it's based on the alpha shape. So some slides before, we already saw an alpha shape. And here's the definition of an alpha shape. It's the basis of this visualization. So what do we want? We want, for a certain time window, that our data structure reports us this polygon shown in pink. And now, in order to know which alpha shape we should report, we need to look at the definition of alpha shapes. This might be a little bit technical, but I will read it out shortly and then explain. The edge PQ is contained in the alpha shape of P if the distance between P and Q is shorter than alpha, and the spatial domain of PQ contains no other points of P. So as you can see here, all of the edges, so these arrows here, they have these circles, these disks, which go through both of the endpoints of the edges, and they are always empty, meaning they do not contain any other point of the point set. And this is the definition of the alpha shape. So every edge that is part of this alpha shape may not contain any other points of the point set. And this makes it very nice. This is a very nice property for us to build our data structure, because we have these edges as atomic elements of our alpha shape, and we can use them as basic elements for our data structure. Because what we can see is we have two alpha shapes for different time windows. In the bottom, we have the time window, and in the left time window, we only contain 1 point more than in the right time window. So this 1 point is not contained anymore in the new time window query. In the top, you see the alpha shape for both of the time windows. And what we can see is that they are very similar. So a lot of the edges that are part of the left alpha shape are also part of the right alpha shape. So it would not make sense to store both alpha shapes independently of each other, meaning we store every edge for both time windows. Instead, what we can do is we can store, since each edge is active for multiple queries, we can store for each edge for which time window queries it's active. And we pre-compute all these queries for which the edge is active and store it. Now we make a little bit of a different visualization. So until now we saw the timeline representation. So here's again the time, and we have this time window query. And now we transfer it to the activity space representation on the right side. Here we have the query start time on the x-axis and the query end time on the y-axis, meaning the interval in the left representation is a point in the right representation. And now when we pre-compute all queries for which an edge is active, we have these rectangular regions in this activity space diagram. So the edge here in the bottom, the blue edge, has associated this activity rectangle in the activity region, which defines for which queries we would show this edge in the alpha shape. And we can decide whether an edge is displayed by checking whether the query which corresponds to the point in this activity space diagram, is contained in the activity region or not. For example, here the query point is not contained in the region, and hence we would not display this edge because it is not part of the alpha shape for this time window query. In the end, we store all pairs of edges that are active for any time window query, and we associate to each edge this information of the activity region. And this is what our data structure looks like. Something else I did, so that was already the main part, the main idea of the data structure. Now there's some extension. So something else I did during my thesis was that I looked at octilinear alpha shapes, meaning we only allow a certain number of edge directions. And we did some theoretical evaluation. So we showed, for example, that the query time is again output sensitive. And we also showed that there's a reasonable memory consumption, which actually later on Funke and Weibrecht worked on again and showed that for a special case, we can even prove a better bound for memory consumption. We experimentally evaluated this approach with this data set of storm events in the United States of 60,000 events. And here are some of the nice visualizations that came out of this project. Some visualizations with the octilinear, meaning here we have a restricted set of directions that are allowed, and also some evaluation of the query time on this experimental data set. But we can show that our data structure, so the pink line, is always, or nearly almost always, below the on-demand version. So especially for larger time windows where we contain a lot of data points, our approach shows to be stable, which is so important when you have these interfaces, that you can always rely on having a fast visualization. Memory consumption seems to be linear, or has a linear feeling to it for this data set. So we looked at different numbers of point sets, and you can see different variants in the different shades of pink and orange. So that was my first part, working on polygonal representations. The second part, as I mentioned before, is the grid-based representation. So now we look at these spatial density maps, which I also mentioned in the beginning at the static visualizations of point sets, and the data structure that we built on it are called, or we called them, theta structures. So let's go back again to what is actually a spatial density map. A spatial density map colors all the grid cells where the number of contained points is larger than theta, or theta is a threshold in this case. And for theta equal to 2, we have this visualization. And now we see that instead of having the edges as the atomic elements of the visualization, now we do have these cells. And we try to build our theta structure on the cells. And we can show that we can build activity regions similar to the activity rectangles before, that define whenever such a cell should be visualized. And in my work, I showed that the activity region of such a cell is a staircase polygon, as depicted here. Now, one can easily pair up the cell with the activity region, and maybe that's it, that's sufficient, but we can even do better. Because, as you've seen before, our visualization is based on this grid. So we do have a spatial structure that actually allows us to build a quad tree on it. So this is what we do. We build on, you have in this figure, you have the spatial grid in the bottom, and we build a quad tree on it so that also the activity regions that we already know for each of the cells are combined upwards in this node, in the internal nodes. So we built these activity regions for each of the internal nodes and also for the root node, and use these for our query. Let's look at how to query. So assume we already computed all of the activity regions for all of the internal nodes. What we do is we start at the root of our tree and we query whether the activity region contains the query point. And if it does, we know this is the sign that at least one of the descendant nodes of this, this root node is colored, meaning it needs to be displayed. So then we need to move down one level in the tree and query again, is there at least one descendant node that is contained in the output? And this is equivalent to, is the query point in the activity region of this node? Whenever we reach a leaf node, we know we can color this leaf node. And this is how we do it for these 4 cells. Now we go to the next internal node and we see, okay, now there's the query point not contained in the activity region anymore, meaning we know that none of the descendant nodes needs to be displayed. So we can neglect all of them and directly move on to the next internal node. And this is actually where we gain a lot of running time if we can leave out huge parts of the quad tree. Something else that we did, or that I did during my PhD, was that I added fractional cascading to this data structure. Might be very technical, so I will not go into detail, but it's another data structure that we can add to our data structure to improve the query time. We performed theoretical evaluation. Here again, the query time depends only logarithmic on the number of events and grid cells, and linear in the number of output cells, which is what we wanted. And the memory consumption is reasonable. We do have n times log m plus m, where n is the number of events and m the number of grid cells. We didn't, or I implemented it, and actually I can show you another video of it. It's similar to the video I showed before of the GBIF database, where you saw that whenever the person changed the time window, it took quite a second or something until the visualization got updated. And here you can see that there's a continuous movement of the time slider possible, and you actually don't need to wait until you don't recognize that there's a latency. Okay, so this is the nice picture. And now there are some more results. So we evaluated the query time. Here you have our approach in blue and pink. The pink one is the one where we added this fractional cascading. Blue is the one without. And the orange one is actually not the very, very simple one. Here we have the grid, and each grid cell already has computed its activity region. And what is nice, our approach, which we expected to be best, is best and actually improves it, especially for the small number of the smaller time windows. So this is a very nice result again. Now we looked at 2 out of the 3 approaches. Let's have a short look into labeling. What is labeling actually? Labeling means you want to display, for example, an icon for some point features. So you want to display, for example, pictures of the birds that you have observed. And as you can see on the left-hand side, typically there's a problem of labeling, that there are too many point features with too many labels. So we call the picture the label. And you need to select a certain subset of the labels or of the point features that can be displayed. so that you have the visualization on the right-hand side, where only overlap-free labels are in the visualization. Maybe just a short reminder, in the very beginning, we talked about the 3 approaches of generalization, and here we do have the selection approach. Typically, then there arises the problem, which of the labels should we use? I mean, there are different options, and it's not straightforward. Normally, you want to have a large number of labels, and if they are weighted with their importance, you want to have important labels in the visualization. Something that now is new for this kind of problem that we have here, since we do have events that have a point in space and time, we actually want to have, again, this time slider interaction, and the labeling should change whenever the time slider changes. And we want to add the consistency criterion to our labeling, meaning we don't want to have a label as the yellow one to appear, disappear, and appear again when we only enlarge the time window. So it would be unreasonable if you have a label being displayed, then you just make it the time window larger. You would display here now the other label, but why would you change back if you make the time window even larger? This leads to a flickering effect on the one hand side, meaning this kind of label appearing and disappearing is not a nice feature of visualization from an aesthetic point of view, but also it is not reasonable. The user would not understand why it's there or not. So this is something we added to in this problem to our formulation. And we developed this lambda structure that guarantees the consistency during basic interactions. That was everything I wanted to say on labeling. Now I will shortly give you a conclusion and outlook on future work. So as conclusion, my research question again, can we develop time window data structures for visualizations of events with a low query time and a low memory consumption? And I showed 3 different approaches for time window data structures for visualizations. All of them are in a low query time, and for the alpha shapes, there are the brackets around the check mark because there is only a proof for uniform distributed labels of subquadratic memory consumption, but all our real-world experiments also supported a reasonable memory consumption, so we are quite happy with this. For future work, I do have 4 topics. So the first topic are different interactions and visualizations for time window data structures are of course also very interesting. So maybe if you have AR or VR visualizations, you need another way of thinking of the data structure. Then there's also other stability criterions that are needed for different kind of interactions. For example, here I wanted to show the panning, meaning you move the map to the one or other side and still the visualization should be stable so that there is no flickering effect. This third outlook topic would be the visualization of data with uncertainties and outliers. This is not always easy because you maybe want to encode the uncertainties that you know about data, or whether maybe you want to know that there's an outlier in the data set and you want to visualize it, but you need to mark this data point. So this is another topic. And at last, I want to mention the aggregation in the temporal dimension. So until now, we only comprise the data in the spatial dimension. So for example, with the aggregation, selection, or the grid-based approach, but also one could think of binning the data points into either data dependent or equally distant time bins. Here's again a list of my publications, and thank you for your attention, and that was it from my side. I'm happy to answer your questions.